All right, so what are the factors that are affecting the rate of solution formation? There are several. They are listed on here on page 569. And the one of the factors is the state of the subdivision of the solute. And the reason for that, if you take a solid tablet and you try to dissolve it as a part of the experiment, let's say, what's going to happen, you're going to see that it will take a little longer time to dissolve this tablet, comparing to if you take the tablet and you actually grind it, you crush it and grind it, and then you're going to try to dissolve now in the same solvent, let's say water, you will see that the powder tablet will dissolve much faster than the solid one. It's because of the now greater surface area, and the solvent can now has more ability and more access now to the molecules of the solute to interact. Now, the second here factor that affects the solubility is the degree of agitation during the solution preparation. And again, it has to do with the solute and the solvent. When you start shaking it, you're giving it a little kinetic energy here, and the molecules now starting colliding with a much greater force, and as a result, they'd be able to interact, I guess, with a higher frequency and forming now these intermolecular interactions, or depending again on the chemistry of the solute. Now, number 3 is the temperature of the solution components, and here you probably notice that at higher temperature, the same tablet, let's say, even if it's a solid, if you put it in the hot water, it will dissolve much faster. And again, it has to do with higher the temperature, higher the kinetic energy, and the molecules are moving much faster. And as a result, they're able to interact in a much faster, more effective manner, solute and the solvent molecules. Now, the part 13.4, the solubility rules. Now, this one is a little trickier again in terms of explaining you guys the solubility of the between the solute and the solvent. And again, I mentioned before, it has to do with the solute-solvent interactions generally, and the likeness or chemistry of the solute should be very similar to the chemistry of the solvent. So the rule here that they're describing, likes dissolve like. It is a correct rule. It works in most of the cases, not all of the cases, and I will be talking about here the cases that this rule does not apply. But generally, if you have a polar substance and solute, and you try to dissolve it in the polar solvent, you will have generally the solute will be able to dissolve in something that is polar solute, something that is polar solvent. Now, if you have something non-polar, such as oil, for example, you will not be able to dissolve something non-polar, let's say in water, which is polar. So you will have two immiscible phases. You will form a heterogeneous solution, and the droplets of the oil will be floating on top of the water. And again, they will not mix because they have different chemistries or different polarity. In this case, one is non-polar, which is oil, and the other one is polar, which is water. Now, the reason the oil floats, of course, on top of the water is because of the difference in densities. And again, we already talked about it in the previous face-to-face lectures. Now, what happens now to non-polar solute and non-polar solvent? So if you take your vegetable oil and you try to dissolve in something like non-polar gasoline, you will see the one that you use gasoline to as a fuel in your car. So you will see how the oil will be actually very, very, very well miscible, or will dissolve in something such as gasoline, because both of these have non-polar. Both of these are non-polar substances. But if you try to dissolve, for example, gasoline in water, you will see they have two immiscible layers, or two layers that don't dissolve, and that means they have different polarity, the substances. And again, water is a polar solvent, and the gasoline is a non-polar solvent. Now, so here now, I'm going to put this book right in front of the camera here. So you got table 13.4, solubility guidelines for ionic compounds in water. And so what this one does is that generally the ionic substances do dissolve in water very well. However, there are some exceptions. And so these rules are telling you, actually, stating the exceptions. And as you can see here, if you look at the, let's say, different substances, so again, I expect you guys to open up the textbook. So I'm going to now use some examples from it. So on page 570, you got this table 570. You will be given this table on the exam, so don't worry about memorizing it. Now, if you take a regular general chemistry class, your professor probably will make you memorize this table, so just be aware of that. But so what is this? What are this table 13.4 telling me? So it's telling me how to read it and be able to figure it out if my ionic substance is actually soluble in water or not. So let me take some examples. Let's say I have some potassium chloride substance, and is it soluble in water? So solid. If I put it in water, what's going to happen here? Well, just want to mention something real quick here, guys. Any ionic substance, all of them dissolve, but some of them dissolve to a very, very small extent, and that's what this table is helping you to realize, which are dissolving completely and which are just dissolving to a very, very small degree now here. So the KCl, would that be soluble in water or not? And the answer is of course. So when you put KCl in water, you're going to form an aqueous solution. So in other words, you're going to see this KCl salt will be just disappearing in front of your eyes as you're adding it to the water solvent, you're stirring it, and it will just go right into the solvent. Now, how do I know it? Look, it says here soluble compounds, and it says group 1A, which potassium does belong to, is always soluble. Are there any exceptions? The answer is no. And you could have also figured it out based on the chloride here. So because you see here now down in this table 13.4, you can locate chloride here, bromide and iodide. So the chloride here also soluble compounds, except for Ag+, Pb2+, and Ag22+, and K+ is not one of these three exceptions, therefore it will be completely soluble. So this one will be soluble. So let me take now a different example. So let's say I have a substance AgCl now, and the question is, would that be completely soluble in water? And the answer is very simple here. If you look at this table 13.4, you don't see here any Ag+ except, oh, look at this, important exception here. But the way I usually do it, I usually don't look much at the cations. I usually locate the anions, which are negatively charged ions. And in this case, I see, oh, chloride is right here. Generally, it is soluble. However, you always have to check for the exceptions. And when you look at the exception here, Ag+, there's your Ag right here, Ag+. It will be one of the exceptions. So what is this now, table 13.4 telling me is that it will not dissolve. So it's not soluble now. Not soluble. And so what you're going to see here is that if you have a flask and you have some water here, so what you're going to see whatever you put in the AgCl inside of this water, you're going to see the undissolved solid in here of AgCl. Now, we can do some other examples. For example, if I have sodium carbonate solid and I put it in water, would that be soluble? Well, the answer here is very easy. Well, first of all, the carbonate here, it's insoluble compound, but group 1A, which sodium belongs to, is always soluble here. It's always an important exception here. And again, once you see the 1A group with anything, it's always soluble. So we'll definitely have Na2CO3 solids here. That will be actually not solids, my mistake here, will be aqueous here. And that would mean that it's soluble. So anytime you're going to see a solid here, it means insoluble. It means solid will be still there. But here what you're going to have is the solid here in equilibrium, guys, with the Ag+. Some of the Ag will dissolve, very small amount, and so you will also observe the Cl- ions in here. So, but the equilibrium will be in that side of the solution as AgCl solids in equilibrium with its ions. But again, this will be more than 99% in here, and these ions will be much less than 1%, okay? Just beware of that, guys. So these will be very, very small amounts here. But this will be almost 100% as a solid here inside of this heterogeneous solution. Let's take a look at another example here. So you got now calcium carbonate solid. And the question is, would it dissolve in water? And the answer is very simple. You go, find the calcium carbonate. It's insoluble compound. And you can see now calcium is one of the exceptions. And the answer is no. It's only ammonium ion. And group A, 1A, calcium is group 2A. So therefore, this will be insoluble. Okay. So now we can do a couple of more examples. You can guys look at now into example 13.1. Actually, we'll talk about it in a moment. But let me use some other ionic compounds. Use this chart to predict the solubility here. Let's say, is my magnesium hydroxide soluble or insoluble? And the answer is, again, straightforward. You're going to find the OH. And OH is insoluble compound, so it's insoluble. And you're going to look always for the exceptions. And the magnesium is not one of those exceptions, so therefore this will be solid. In other words, it will be in the equilibrium between, in the solution, this aqueous plus 2OH minus. And again, don't guys worry about this, what I'm writing here. All you have to understand that you have to just say it insoluble. And that's what will be asked on the exam, whether it's soluble or insoluble, just using the chart. And all you have to do, just choose the correct answer. You don't have to worry about this equilibrium equation, guys. Now, next one, we can now do, for example, let me just come up with some problem here. Let's say potassium phosphate. And again, if you examine this chart in here, table 13.4, it's actually a table here, you're going to see that anytime, again, phosphate is insoluble. However, anytime you got 1A metals, it's always soluble. So you will have the potassium phosphate solid dissolved in water, guys. Okay, now, so this is how to use this table 13.4. So now we can do example 13.1. Example 13.1. All right, let's read this example. Predict the solubility of each of the following solutes in the solvent indicated. Now, ammonia. So you see, they actually state the polarity of the ammonia, which is very good for us because remember, we never learned how to determine the polarity of the molecules. So ammonia's formula is, of course, NH3. And benzene, and they say benzene here, they're telling you right away it's nonpolar, which is correct. And the molecular formula will be C6H6 in here. And so remember, guys, the rule, if this is polar, this is non-polar, these two don't mix because they have different polarities. Okay, so they will not be miscible. That's the term we usually use. But to be very simple, it's pretty much you can use soluble or insoluble here. And ammonia, of course, will not dissolve here in benzene because they have different polarities. What about now sodium bromide? Sodium bromide, ionic solid in water, in H2O. Here you will have to go to table 13.4 to predict it. Anytime you have ionic substance and you want to dissolve it in H2O, this is the table to use, 13.4. So it's a very simple answer here because sodium is in 1A. In 1A, it has no exception, so everything will be dissolved. And the answer is, of course, sodium bromide will be soluble in water. The next one is calcium carbonate. I think I already covered this in the previous discussion here. So the calcium carbonate, of course, will not dissolve in water according to the rules here, solubility rules in table 13.4. Because if you can see now, the carbonates are generally insoluble. And then the exceptions, only ammonium ion and group 1A elements. Now calcium is not 1A, it's 2A, and therefore they will be insoluble. Now next one is AgCl, and I already covered this one accidentally. So again, this is ionic in water, and you have to, guys, always refer to table 13.4, which a similar table will be provided, guys, in the exam. So just make sure that you know how to use this table. And again, if you got Cl minus here, the chloride, You're going to find it here in the under soluble compounds, and the Ag plus is an exception, so therefore this will be insoluble as well as the calcium carbonate.